Hello everyone, welcome to the official YouTube channel of askIITians, and I am Anik Ghosh, senior chemistry faculty over here. Today guys, you are watching the first video of our P-block series. Here I'm mainly gonna focus on the group 13 and group 14 and the grade 11 part of this P-block, right? Specifically guys, in this video we are gonna make it specifically for group 13 only. And definitely over here, as you know, in JEE, you have certain part of group chemistry, but in JEE Mains, what I'm meant to say is, and in JEE Advanced, you have the entire group chemistry. So as a result, guys, we have to mention. I'm gonna mention that as well. We have to understand which all parts do we have to prepare for when you're preparing for JEE Mains, and similarly for JEE Advanced as well. See, JEE Advanced means it's the entire syllabus only, but for JEE Mains, the syllabus is pretty much shortened, pretty much rationalized. So based on that, guys, we are gonna go for it. So first of all, I'm gonna show you what is the part which is there in the JEE Mains syllabus. So as you can see, so I'm presenting my screen with you. Let me check whether it is working or not. Yeah, it is there. All right, so as you can see, guys, in this part in the inorganic chemistry, if you just open up your syllabus, in the inorganic chemistry part, the P block group 13 to group 18 is mentioned in there. But guys, when you look into details of this topic, which all topics are included in there, you'll be able to see the electronic configurations are included, general trends of in the physical and the chemical properties of the elements across the periods down the groups, and the unique behavior of the first element of each of the groups. So guys, they have only 1/4 part of every single chapter. What I mean to say is, let's say we talk about grade 13 right now. So for that, let's go to this NCRT. In group 13, if I see for JEE main syllabus, they have this first part. Okay, starting from here, they have this part. These are all these things: atomic radius, ionization enthalpy, electronegativity, physical properties, chemical properties. These are all there in your syllabus. Electron efficiency, reactivity towards acids, alkalis, reactivity towards halogen. Okay, these topics are all there in your syllabus. Then important trends of the anomalous properties, important trends and anomalous property of boron. Guys, this is where your syllabus gets over for group 30. Similarly, for group 14 as well, when you open it up, you'll be able to see the same heading is there for group 14 as well, important trends of the anomalous property of, then in that case, it would be carbon. Remember one thing, guys, for every single group chemistry, the first element, like for group 13 is this boron, group 14 it would be carbon, group 15 it would be nitrogen, group 16 it would be oxygen. For all of them, they show anomalous property. And that's why this is a common point which is there in every single chapter. So that is up to that only you have to study. Rest of the part, like the borax, then orthoboric acid, and all these things, these are not in your JEE Mains syllabus at all. So these are all there in your JEE Advanced syllabus. Let's talk about group 14 over here now as well. So if I'm talking about group 14, this is where the chapter starts. So you have ionization enthalpy, electronegativity, all these things are included till oxidation states, reactivity towards air, catenation. There you see. Important trends and the anomalous behavior of carbon. Like I said, for every single system, the first element is gonna show important trend and anomalous property. So till there you have. So every single chapter you have only 3 to 4 pages in your syllabus, right? But in this video, I'm definitely gonna teach you all these things for sure. But then again, guys, I'm gonna teach you the entire chapter as well, because for some of you, those who are preparing for JEE Advanced, this video would be more than sufficient for you guys. You can watch this video, and after that you can read it through the NCRT. There are some extra topics that I'm gonna teach you here as well. Those you can get from any standard books, right? For example, you can get it from Crabtree or JDV or any of these books, inorganic books. You can find those questions from there. Okay, so now let's get started with the topics in here. So guys, before we get started with the topics of the chapter of this P block, there are a few things which are common in every single groups actually, right? Few concepts are there. Starting from the first concept, which is very important for group 13, group 14, group 15, right? All the three groups. This is very important topic. That is called the inert pair effect. Okay, so that is where we can start. We are gonna start. Guys, you can definitely watch this video in 2x speed just to save some time. Inert pair effect. But make sure you take these notes, because in the book it is not really well explained that much. Okay, definitely you will be able to understand it, but here I'm trying to give you the best way of explanation that I can do. Now, what is inert pair effect? Let's talk about that. First, let me tell you what is the effect. Okay, the effect was like this for group 13, group 14, and group 15. For these three groups, what we see is the last element. For these three groups, the last element. That means thallium, lead, and bismuth. What happens to these three elements? They show two less valency than the group valency. What do they do, guys? Two less valency than the group valency. That means the group is 13. 13 means every element are gonna show three valency. That's the shortcut, right? Whatever is the group number, minus 10 is the valency. For group 14, guys, carbon would be 14 minus 10. So that would be 4, like that. Correct. So that is their valency. Now, which valency are we talking about over here, guys? We are specifically talking about covalency. You know that there are two types of valency, covalency and electrovalency. So we're talking about covalency here. Now, so this guy is supposed to show the valency of 3, but thallium shows the valency of +1, 2 less. For carbon group, lead shows the valency of +2, and bismuth, this shows the valency of +3. You can see that it is 2 less than the group valency for every one of them. Now, this particular thing that two electrons are becoming inert, because see, when we talk about valency, we are talking about reaction. When I say that the system is getting inert, that means, guys, what I'm trying to mention is like the two electrons are not really valence electrons anymore. Correct. This is what I meaning there. Now, understanding that, we can say two electrons are unable to participate in a reaction. To participate in reaction. Two electrons are unable to participate in the reaction. Now, this particular thing is known as IPE, inert pair. These two electrons, they are called the IPE. Now the question is, guys, what is causing this inert pair effect, right? Why is the inert pair effect coming in the first place? If you feel like you know this inert pair effect, guys, you can definitely skip this part of the video. Okay. Now, the reason behind inert pair effect. So we have to start with the topic called shielding first. Now, what is shielding? So we know that, let's say this is my nucleus. There are some shells in there, and this is an electron over here. Let's say the nucleus has the charge of 10. Okay, there are 10 protons present. So the charge is +10, right? But the nucleus, the electron over here, that is it, that would be not experiencing the exact +10 charge. So what happens is, let's say this is the charge shared by the nucleus. Some of the charge would be screened by the first layer, would go to the second layer, a little less. Then the second layer would screen a little bit of it, then the third layer. So let's say we started with +10 charge, maybe the electron would feel or would experience only +6 charge, because some of the charges would be shielded or screened. Now, this particular nuclear charge is called Z, and this one is called Z effective or Z star. What you send is nuclear charge. What nuclear has, that is called nuclear charge. And what the electrons experience, that is called effective nuclear, because rest of the nuclear charge is just going in vain, right? Because of the screening and all. Now, we can write the Z star equation as Z minus S. We can write the equation of Z star as Z minus S. Correct? Because here, according to this question, 6 is equals to 10 minus S. Because of the things that got screened or shielded, how much of them got shielded? Then 4. Because 10 minus 4 is equals to 6. That's how we understand what is the process of shielding. Now, shielding and screening are the same thing. Screening capacity order. Screening capacity order goes like S the most, then P, then T, 10. Screening capacity order goes like S, P, D, F. S has the highest screening power, then P, then D, then F. Okay. Now, why is it so? Because, guys, you know for a fact that the S subshell has a very condensed structure, whereas P is a little bit more diffused, right? D is even more diffused, right? So, more you move from S to P to D, you can see that what happens is the diffusion on the orbitals that is increasing. As the diffusion is increasing, so the orbitals are very far away from each other. It's very, very, diffused, I should rather say. So because they are diffused, they cannot screen much. It's a very simple thing, guys. Let's say if you think about, if you imagine about, there's a thin piece of cloth in front of a bulb. Okay, so the bulb over there, the type of light that the bulb would generate, and from that light would be somewhat shielded by the cloth which is kept beside it, about like in front of it, right? Now the cloth, if the cloth is very thin, then the blocking of light would also be less. But if the cloth is very, very thick, then it would block more amount of light, correct? So considering that, we can understand, as the thickness or as the density wise, S subshell is the highest, so that means its screening power is also going to be highest. Okay, so if the screening power tendency is this, then screening or shielding capacity tendency is this, then Z star tendency can be written as F D P S. What do I mean by that? Guys, you know for a fact that Z star can be written as Z minus S. Z star equals to Z minus S. Right? So if somebody has a high screening power, then definitely the Z star goes down. Correct? It's opposite to each other. So from that there only I am saying SPDF's Z star tendency would be opposite to that order, FDPS. Okay? This much we are clear? Now, so what is the conclusion of the story? D and F block elements show highest, this D and F block elements shows highest amount of Z star values. Okay, so D and F block elements, they are capable of showing the highest amount of Z star values, because guys their screening capacity is very, very less, so their Z star values are very, very high. Right? Now, what can this high Z star value cause? Let's talk about that as well. So as the Z star is high, we can say that Z star, this is equivalent to the nuclear charge. We also call it the effective nuclear charge. Nuclear charge or the effective nuclear charge, same thing. So as the Z star value is increasing, that means the nuclear charge is increasing. If the nuclear charge is increasing, then what do we get to see, guys? We see that the atoms, their electrons faces a lot of attraction power because the nuclear charge is increasing. Because that attraction power forces them to shrink. The atoms, they become smaller in size because of that, guys. Okay, so D and F block orbital elements, they shrink down to smaller sizes because of the high Z star. And do we know what do we call this, guys? We call D and F contraction. Correct? The nuclear charge is high. So from there we can write the atomic radius decreases. The atomic radius would decrease, or atomic radius decreases. Because atomic radius decreases, we call it D and F. D and F contraction. Okay, contraction. This is called the D and F contraction. Okay, this is something we have learned in D and F block as well. Right. So this is the first thing, guys. What is the DNF contraction? Now from here we are going to go to the inert pair effect. Okay. Now I want you to imagine how does the periodic table look like. If I look at the periodic table, okay, let's say this is the periodic table. All right. Now see, let's say this is boron. This is aluminium. I'm talking about group 13 right now. This is where helium and hydrogens are. Okay. So boron, aluminium. Then we have gallium. Then we have indium. Then we have thallium. This is how they are. Right. Now here we have before gallium, we have 3D series elements. Before indium, we have 4D series elements. And before thallium, we have the 5D series elements. Right, guys? And you know what? Exactly in these two positions, which elements are present? Lanthanoids and the actinides. They are present in exactly in those two positions. Okay, let me just see once. I believe it would be like this. Lanthanoid and actinides. Actinoids are even below that. Lanthanoids are in the 5D series. Okay. This goes like scandium, yttrium, lanthanum, actinium, like that. Okay. So this is how they are. This is how they look like. Now, if you notice thallium, that if I talk about group 14 and group 15 as well, thallium, bismuth, and lead, all three of them are the last element of that group, if you notice, right? They're the last element of that. Now, what is that suggesting us? As they are the last element of the group, what is that gonna affect? How is that gonna affect? See, as you can see, there are F block elements here. Lanthanoids are F block elements, correct? And these are the D block elements. So these people, this thallium over here, this is a victim of D plus F contraction. It's not only one contraction anymore. Thallium, bismuth, and lead, they are experiencing D plus F contraction. D contraction, though, that is there anyway, but F contraction is also getting added up in there. As a result, because of the D and F contraction, what happens is the Z star is very, very high. Z star is very high. Okay, the Z star becomes very, very high. As the Z star gets very, very high, as the Z star gets very, very high, it pulls the electron down. It pulls the electrons down. So you can understand when the nuclear charge is increasing, that would definitely pull the electron of the shells down, closer to them, right? So this is what the Z star is trying to do as well. Pulls 6 electrons to make it inactive. Okay. Plus 6s electron, pulls 6s electron to make it inactive. Okay, this is a part where we are going to talk about actually. So what happens is, if I talk about thallium, thallium is, you can calculate it from here only. So 1s to 2s to 2p1. So this 3, 4, 5, 6, 6s to 6p1. Right? Thallium is 6s to 6p1. Okay. Now what it does is, due to inert pair effect, due to the high attraction forces, what happens is the 6s orbital, they feel the most amount of attraction forces, and they get stabilized the most, right? And because of that, because of the 6s orbital getting stabilized the most, because of that reason, what happens is the thallium can show only the valency of 6p1. As a result, the valence of thalluminum is shown to be +1, only 2 less than the group valency. All right, guys, clear? Now, similarly, when we talk about the rest of the elements, like this was lead, But similarly for bismuth and this was thallium, sorry. So for the lead and the bismuth as well, what happens is, for what would be the electronic configuration for, if I talk about for lead, lead's electronic configuration would be 6s2 6p2, 6s2 6p2. For bismuth, the electronic configuration would be 6s2 6p3. So for all of them, due to this high Z star, and it is pulling the electrons down, and specifically the 6s electron, they come first, so that they are being pulled first. So as a result, guys, in all these cases, what happens is the 6s electrons, they become inert. So the inert pair effect, what we talk about, that is actually 6s orbital electrons that we are mentioning here. So this is the overall idea, and that is why lead shows +2 oxidation state, and bismuth shows +3 oxidation state specifically. Now, this was, guys, our inert pair effect, concept of inert pair effect. That would be very, very important for us. We're going to the group 13, group 14, as well as in group 15 as well. Now, the second concept that I'm going to go for is called the Fajan's rule. This is also very, very important for this topic, for this particular group specifically. The Fajan's rule. Now, what is this Fajan's rule here, guys? See, Fajan was somebody who said, a scientist who said that, like, there is no compound out there which is 100% ionic. There's always some sort of covalency in an ionic compound. So every ionic compound has some covalency in it. Every ionic compound has some covalency in it. This is what the Fajan's rule is saying. Similarly, guys, every covalent compound has some ionic character in them as well. So like I was saying now, for Pauling, like Pauling said that every covalent compound has some ionic character, just the opposite of it. Every ionic compound has some covalence in it. That was said by Fajan, and the opposite was said by Pauling. Okay, so Pauling series and Pauling compounds have been discussed in grade 11, actually, in periodic properties, right? Now here in the Fajan's rule, what do we learn, guys? Let's say I have a compound which is NaCl, and I have another compound which is AlCl3. What would be the difference in here? Guys, we saw that the NaCl's melting point, that goes up to 900 degrees centigrade, whereas for AlCl3 it has been seen which goes up to 100 degrees and even lower than that sometimes, right, in some of the compounds. Now, if I talk about this reason behind it, if you see that these two values are trying to tell you something, trying to tell you a small story here, because if you notice, whenever there is a high melting point, that is supposed to be for the ionic compound, because this is an ionic compound. So we are supposed to see a high melting point and a high boiling point. But AlCl3 is also supposed to be an ionic compound, correct? Because it is also metal non-metal compound only. But guys, the melting point has been seen somewhere near to 100 degrees centigrade. So what is causing this, right? So from there, we started looking into it, and we found that AlCl3 is not at all an ionic compound. It is actually a covalent compound. It's actually a covalent compound. But how can AlCl3 be a covalent compound, right? That can be an important question coming in your mind. So here's the thing. What Fajan said is, let's say this is Na and this is Cl minus. Okay. Achha, obviously, the cations would be smaller than the anions in size. And this is Al3 plus, and this is Cl minus. Now, what they're saying is, when you have a high plus charge in your compound, they attract the electron cloud, deform the electron cloud to some extent, and that can create some sort of overlapping in an ionic compound. And the moment you see the overlapping is there, it is a covalency, right? So here we see overlapping. That means that generates. So guys, the point is very, very simple. There are some ionic compounds that those who have a very high plus charge in their cations, they can deform the electron cloud of the anion, although they are supposed to be separated. But guys, the plus charge that is called polarizing power of the cation. So polarizing power of the cation of Al3 plus is pretty much high because of the high ionic charge density present in it. Charge density, according to Pejana's rule, can also be given as this phi symbol. This is called charge density. Now, as the aluminium has the high charge density, as a result, guys, the degree of what should I say, like deformity of chlorine electron cloud, that is most in case of AlCl3, and as a result, it creates some sort of covalency in it, and this is called the Pechans rule, right? So this was the second thing that I had to discuss with you. Now, the third conceptual topic and the last conceptual topic is characteristics characteristics of oxide. Characteristics of the oxides. Okay. In the characteristics of the oxides, what we are actually trying to understand over here is that, let's say I have a metallic oxide. What are characteristics are we going to see it in that? Let's see, metallic oxides are actually basic in nature. Whereas if I have a non-metallic oxide, those are seen to be acidic in nature. Non-metallic oxides are acidic in nature, and metallic oxides are basic in nature. Now, this is something we can easily understand by an example. Let's say I have a metal which is sodium. The oxide of the metal would be Na2O. Guys, when we dissolve Na2O in water, you get NaOH. So from there, you can clearly understand the metallic oxides are forming bases or alkalis. So they are basic in nature. Whereas if I have a non-metal, the oxide of it, if I just dissolve it in water, I am getting H2CO3, which is carbonic acid. So it is acidic in nature. Correct. Now, there are some metallic oxide, those who are also amphoteric. Guys, I believe you remember it from grade 10th that there are metallic oxide like ZnO or Al2O3. They're amphoteric. So they show both the characteristics of acidity and basicity, both combined together, correct? So these are called the amphoteric oxides. So generally the metallic oxides are found to be the acidic in nature, basic in nature, but they can be amphoteric as well. And non-metallic oxides are generally found to be the ones those who show acidic character more. So they're acidic. So this is what we have to, this much of understanding is what we need about this chapter before we get started with it. Now let's jump into the topics one here. So in today's video, guys, I'm gonna mainly, like I said, I'm gonna mainly focus on the group 13, okay, of the P-block elements. Now, let's talk about the electronic configurations first. So when we are talking about the group 13, guys, in terms of electronic configuration, you're going to see a similarity in the electronic configuration there. Achha, first of all, which all elements are there in group 13? As you can see, this group is called the group 13, boron, aluminium, gallium, indium, and thallium. How do you remember this, guys? Bangan, alu, gajar, in thali. Correct? Indium, thallium. Now, boron, atomic number is 5. So electronic configuration goes like 1s2, 2s2, 2p1. Similarly, aluminium's electronic configuration goes like 3s2, 3p1. Gallium's electronic configuration would go like 4s2, 4p1, because guys, we are just going to increase the shell one by one. Indium 5s2, 5p1, and thallium would be 6s2, 6p1. Correct? Now, if I have to make a generalized electronic configuration, so I can write ns2, np1. This is the electronic configuration of all the group 13 element. Now, if I talk about group 14 elements, for them, what are we going to see? Carbon, silicon, germanium, tin, lead. Similarly, guys, for these people, this is 2s2, 2p2. This would be 3s2, 3p2. It goes on like that. So for group 14 people, we say we are going to go like ns to in. Okay. So these are the general electronic configuration of group 13 and group 14. How to remember the group 14 elements? It goes like, chemistry sir gives Sunky problems. Sunky means crazy, mad, right? So this is how we can remember the group motivation here. Now, inert pair effect is something that I have explained in a minute ago, guys, to in the very beginning of the video. So you can refer to that video to understand this inert pair effect again, right? We're going to watch a small recording, small video on this as well. So to get a better idea and in the understanding of inert pair effect, guys, okay? So just let me share my sound here.
The inert pair effect.
Okay, guys, I'll be explaining this to you, okay? So as you can see, the configuration explains the inert pair effect mainly for the people, those who are there in the group 13, group 14, and group 15 elements, right? You can see the names of the elements. There is one more thing that is there. Other than the last element of these groups, they're also, let me see, other than the last element of the group, they are also focusing on the second last element as well. Guys, see, it's just like after effect. So mainly the inert pair effect is shown by these last elements, but the second last element can also show a bit of it, right? It's not like that powerful like that is in that last element, but the second last elements like indium, like tin, and like their antimony, they can show a little bit of it as well, right? Right. Huh. See, they're going to say the same kind of thing in there. They're just taking antimony as an example here. But we're going to take the understanding of lead example that I've been telling you as well. So for lead, as you can see, the electronic configuration is 6s to 6p2. The 4f and the 5d orbitals in between, they are actually energetically lower, right? 6s is energetically higher. So as a result, when the electrons, when we are talking about the electrons of formation of Pb2 plus, they are going out from the 6p, correct? From here, we are taking the electrons out. But we cannot take out the electrons from 6s anymore because that is deep seated. That is because of the high Z star which are present in the elements, right? Because they are the D block elements and the F block elements beside it. So because of that, these two electrons, those are then the P block, P orbital, they are capable of losing the P electrons, but not the 6s electrons. They are deep seated inside, right? This is the main thing. Because if you had to take out, as you can see here, because of the writing, I believe it is a little bit difficult for you to understand. Let me see if I can. Yeah, now you have a look. If they have to, lose the two more electrons now after Pb2 plus to Pb4 plus, they have to actually lose the 6s electron because 6s is energetically higher. Those are the electrons that they go out. But right now, because of the high Z star, the 6s electrons are not accessible anymore. They are not going to be donated anymore. So this is called the inert pair effect here, right? I believe that we have a better understanding with this topic anyway. So guys, like I've been discussing, so because of the inert pair effect, what would happen is, let's say for group 13 elements, in that, let's just focus on this picture. So let's say over here, the boron that I have, it would be showing the valency of 3. Aluminum would be showing the valency of 3. Gallium would be showing the valency of 3. Now see, indium, what would have happened? Indium can show +3 and +1 both, whereas thallium would only show +1 valence because of the inert pair effect. And I told you that the second last element would also have some effect of it. That is what you can see right now. Now, similarly, if I talk about this group 14, everybody shows valency 4. Silicon also shows valency 4. Germanium also shows valency 4. But when we come to tin, it can show valency 2 and valency 4. And lead can also show only valency 2 because of the inert pair effect only, right? So this is the main topic of discussion about the oxidation numbers that we get to see. And on the basis of this now, you're going to see that going forward, you're going to see so many questions are coming. Why SN2 plus is acting like a reducing agent, whereas PB4 plus can act like an oxidizing agent? These kind of questions can come a lot, right? Where you have to just use this inert pair effect concept to in order to answer, right? So this is the main part here. Now let's talk about the nature of the oxides, guys. Now I have told you, whenever we are talking about the oxide nature, you have to understand whether whether it's a metal or non-metal. Like if I say the oxide of boron would be B2O3, right, guys? Because the valency of boron is 3 and the oxygen is 2. So what we do is we crisscross them to find out the compound. So B2O3, Al2O3, Ga2O3, In2O3, Tn2O3. Basically, what we see is B2O3, as it is not even a metal, guys. So it's kind of a non-metal, correct? So we see that this particular thing is acidic in nature. Al2O3 is amphoteric. It shows both acidic and basic. Since then, the acidic characters, the basic character. Okay, basic characters. So because the metallic character, because more you go from, gallium is also amphoteric in nature. Okay, gallium and aluminium. Indium and thallium are basic in nature because they are metals. Indium is also metal, thallium is also metal. Okay, so that is how we can understand the nature of the oxide segments. All right. Now, guys, the next thing, anomalous property of the first element of every single group. See, right now, what I'm doing is, if you could understand, I am giving a generalized idea about both the group 13 and group 14. I'm not teaching you any of the groups specifically so far. I'm teaching you both the groups combined together. Right after these basic things which are common in both the groups, when they are done, then I'm gonna talk about specifically in the groups as well. But guys, if you wanna know till when do you have in your JEE Mains, it is till here. Okay.